Hello Precalculus. Today's video, I am going to finish up the notes that I started for, I think it's the day 129 document. I did not talk about how to describe the continuity. I did not talk about the describing the c values for which the limit as x approaches c of f of x equals 1, things like that. I also did not talk about inverses, which this will be a nice segue into maybe me going back and explaining through video the last part of the function composition chapter about inverses. So I'm bringing back up the notes for day 129. You guys should keep that in front of you for reference so you can see it in greater detail. I am going to talk about the last few items on there. So you can't see it in the video, but it says describe the continuity of f of x, describe the c values for which the limit as x approaches c of f of x equals 1, and then explain why f of x either does or does not have an inverse. All right, so I'm going to get rid of that little graphic there and use some room off to the side to write my answers. So if we do a little maneuvering here, I believe that gives me more. Hey, look at that. I got plenty of room. Let's actually work backwards. Let's talk about what is a requirement for an inverse. Well, what I tried to communicate to you guys before spring break was that functions are one-to-one if they have inverses. And what one-to-one means is that exactly every single x element, so kind of everybody who rides on the x-axis, okay, maps to exactly one y element, and vice versa. So you can't have a y value that corresponds to two x values on this graph. So the fact that the y value, you guys maybe can't see it very well, but this is our origin. I'm really struggling with this right now. Give me a moment. I will succeed. All right, that's good enough. Okay. So like right here, 1, 2, 3, 4, 5. Y equals 5 when x equals 1, when x equals 123.6, when x equals 4.1, when x equals negative, I think, negative 7.6, the y value is cheating on those x's. Okay, so an inverse function, a function that either has or has not an inverse, is based on the horizontal line test, the one-to-oneness test. No, it doesn't pass the horizontal line test. It is a function because it passes the vertical line test. For every one x, there is exactly one y value. I wish you guys were here so I could explain this a little more in depth. That's okay. I'm going to move on, though, to I think I'm going to talk about continuity next. So what is continuity? Well, it's kind of like if you ever watch a movie, okay? And let's say like two people are talking in a cafe in a movie, and in one scene it shows maybe one actor's reactions, and he's holding a cup of coffee. And then it shows the other actor. And then when it's back to that first actor, the cup is gone. It'd be like if I were editing this video and I'm just talking to you and all of a sudden it stops and this marker's not in my hand anymore. That would be an error of continuity. That means that they basically digitally changed the movie so that it did not keep rolling in the way in which it was filmed. It's kind of like that with functions, okay? If you can just keep a steady movement along the function, basically without keeping your pencil off the paper, without taking your pencil off the paper, you're fine. But once you have to stop that to get the next piece of the function, see right here, I'm moving along and I have to lift my pen from the marker board to basically put another element of that function on there. And then I got to start over again. That's an error in continuity for this function. It is not continuous at this specific x value right here. Similarly, if there's a hole in the graph, all right, I'm not pulling a Carl Lewis and jumping over the hole. I have to stop. I have to move over the hole. Well, maybe I am pulling a Carl Lewis. There's basically no continuity. I have to stop and then start again. Stop, start again. Eventually stop and start again. So I hope that's on a basic level a pretty good idea of what for you guys of what continuity is. Continuity is when the graph basically stops for an asymptote or a hole in the graph. So, where do we have continuity issues? We have continuity issues at this asymptote, which is negative 1, 2, 3, 4, 5, 6, 7. So, we would say it's discontinuous. Actually, I got an idea here. It's discontinuous at x equals negative 7. It's also discontinuous at this hole in the graph at negative 1, 2. I'm going to put it down here, though. You'll see why in a little bit. So this was discontinuous at x equals negative 7, discontinuous at x equals negative 2. Remember, we're talking about the x values. The x values we're defining the continuity issues of. We're going to have another discontinuity at x equals 1. I'm going to pair it off with this negative 2, though. And right here, I've got a discontinuity at 1, 2, 3, 4, at x equals 4. That's going to be the one that goes with the negative 7. And then right here, 1, 2, 3, 4, 5, 6, 7, at x equals 8, we have another discontinuity. And that one's going to go with the top one here. Now, the reason why I grouped these three discontinuities together and I grouped these two discontinuities together is that they represent two different types of discontinuities. Okay? This first type of discontinuity is called a non-removable discontinuity. So, this is a non-removable discontinuity. And the most basic definition for a non-removable one is that the limit doesn't exist there. So for this right here, the limit does not exist at, I'm just going to say an NRD, non-removable discontinuity. And hopefully that's clear for you guys. Anytime you have an asymptote, the limit's not going to exist there. Anytime you have a clean break in your graph where you'd have to build a bridge vertically to get from here to here, that's also going to be a DNE, a does not exist type limit. Now on the bottom, we call these removable discontinuities. That is where a limit does exist. It's sort of like, all right, the function itself stops and then restarts again, but the limit itself does exist, okay? So the limit does exist at, and I'm just going to call it an RD. Now, to make things easier for you guys, I'm just going to let you guys say NRD at x equals -7, or +4 and 8. RD at x equals -2 and 1. And I mean, right now that's not the most sophisticated way in which to communicate where the discontinuities are, but it's an easy way for you guys at this point just to write down your answers. So we'll communicate that way. Alrighty. The last question. It's really wordy, and it has confused students for the past decade for me and beyond. It's something like, well, let's bring it back. Describe the c values for which the limit as x approaches c of f of x equals 1. All right, so what I'm going to do is erase all this. If you didn't get it copied down, pause the video, rewind it. All right, so describe, that is not a B. The c values for which the limit as x approaches c of f of x, which is this whole graph is f of x, where that equals 1. Now this is very interesting, because what it's saying is it's saying, where does your limit equal 1? Where does the limit equal 1? So where does the function approach a y value of 1? Which is kind of like saying, maybe we should draw just a horizontal line at y equals 1 to like visualize this thing. So here's our origin. 1 is right here. So where would the limit equal that line? Well, right here. From the left of this x value and from the right of this x value, even though there's not a hole in the graph, that doesn't mean that the limit can't exist there. In fact, anywhere where a function exists from the left and the right, like if it's defined there, that's totally fine for a limit. So the limit as x approaches, it looks like about -0.5 to me. That's a perfectly legitimate c value. The limit as x approaches -0.5, okay, equals 1 of that function. So c equals -0.5. There's one of them. Can you see any other ones where from the left and the right they converge to 1? How about right there? As x approaches 2, from both the left and the right, it converges to a 1 value for its y. Any others? Oh, this one right here. Okay, I can't really tell if it's exactly 1, 2, 3, 4, 5, 6. So we'll say it's about 6.1-ish. All right, now here's the one that's really a little bit tricky. What do you make of the fact that as c approaches -infinity, as c approaches -infinity, is that equal to 1? I mean, go back to your notes. We said that the limit as x approaches -infinity, that is getting closer and closer and closer and closer to the value of +1. Now the question is -infinity a legitimate c value? Did I put any restrictions on c values? Does a value have to actually be like a tangible finite number in hand? And what do you think?